Super. Okay, yeah, so punning title. So of course, footprints are a key concept in reasoning about state. And this is going to be a slightly self-indulgent chat about sort of the last 30 years of my following along after things that Pete's done already. So several other people have put up when they first met Peter. I'm reasonably certain that this was when I first met Peter. It was a workshop in 1995 on syntactic control of interference and linear logic, organised by John Reynolds and Phil Wadler. Took place in Glasgow, I guess. Yes, and yeah, so this was when the first idea of taking syntactic control of interference and realizing it had some similarities with linear logic kind of came on the scene. And it's a nice list of invitees here. I was particularly amused by the fact that the call for participation includes the names of all those people who had declined the invitation being shared with everybody. I thought it's rather good. So at this point, to be honest, I've been working on linear logic for a while, and I was really interested in it as an abstract system, categorical models, proof theory, this kind of thing. Not all that much in applications, if I'm honest. So I was a bit of a naive, idealistic functional programmer at that point. I think Derek admitted to something similar, that when you're young, yeah. But I didn't have Derek's excuse of only being 12 at the time. So yes, I mean, this was very interesting, but I wasn't really excited by the applications to state. Though Phil and I did actually do something on the last question raised there. But then, bunched implications came on the scene with really quite a bang. And this was an extremely memorable meeting. So linear logic and its applications. This was still about linear logics. And it was in '99. And at this point, Pete and David Pym and Uday Reddy arrived at this meeting of linear logicians with bunched implications, and they were taking no prisoners. So this is the write-up of that meeting, and you can see that. Controversy happened. It was very good-natured. It was very exciting, but there was a real sense that there was a new kid on the block, and that many of the claims that have been made for linear logic as a logic of resources were kind of open to question at the very least. Yeah. I particularly like there was no agreement that linear logic was devoid of interest, which was pretty exciting stuff. So yeah, and about this time then we started having quite regular meetings between Cambridge and London, and meeting up with the East London Massive. And I got to meet Josh, which was truly wonderful. And Josh did actually write a PhD thesis which had linear logic somewhere in it, but I think he denies any connection at the moment. Who fucking cares? Okay, but I was working with Andrew Kennedy on a compiler for standard ML at this point, and standard ML is unfortunately not a pure functional language, and so we put an effect system in there which tracked the impure stuff, and we used that for optimizing transformations. And I got interested in the question of why were these transformations on the programs correct? So we actually had a paper in 1999 which did actually succeed in proving, using some horrible operational techniques, the correctness of those transformations, but I was never really satisfied with that. So then the next bombshell, 2000, 2001, along came separation logic, and I guess everybody in the room knows something about separation logic. I have to say I was still a functional programmer, and the real lesson I got from reading this at the time it came out was actually program logics are more interesting than I thought. Not the details of separation logic, but just the very idea that program logics were worthy of study. Because it seemed like it was very moribund, right? I mean, brilliant papers in the first place, and then For a long time, there was no progress. So people who worked on what was called formal methods didn't really seem to be getting anywhere. And then suddenly, Pete and friends kind of put the whole thing on a respectable footing and actually understood where the quantifiers should go and all sorts of stuff like that, which was kind of interesting. And then there was a paper in Popple on proving correctness of compiler optimizations, which annoyed me so much that I went back to the problem of proving the correctness of optimizing transformations. So this was the first paper that came out of that. This was, for those who are in the know, this was originally called Proving the Correctness of Compiler Optimizations Without Temporal Logic. So this was the thing that got me into the idea of caring about state and reasoning with relations, logical relations. And so this paper has a relational version of Hoare logic in it, and I would never have dreamt of touching something that looked like that had I not seen Pete's work on separation logic, even though there wasn't separation in this particular version. But I got really interested in reasoning about state. And so this was for a while language with no allocation, and then I moved on to the exciting problem of looking at equivalences in languages which had store, in fact, dynamically allocated to store. So this is something that it turned out, once I started looking at this, it turned out really that the key ideas were there in work that Pete had done a long time ago, and Hongsek already gave us a talk about how beautiful this paper is. But the basic idea is that independence and the idea that you can only access something through an interface kind of works at a logical level the same way as it does at a type level. So the ideas of parametricity which were being developed at this time kind of also worked for reasoning about the details of a particular program equivalences. And so this sort of says quite clearly that the fact that if you've got a procedure that doesn't have direct access to some bit of mutable storage, then the way that you say you can only change this by the operations that you have been given is exactly analogous to the way that you prove that a parametric function with a polymorphic type works the same for all the instantiating types. And so these models, I mean, there were a lot of papers on this sort of thing, and they all look kind of like this. And so obviously there's a bunch of gory details here, but what's the exciting thing? So the exciting thing is we've got reference cells, like ref in ML or OCaml, and we're going to give the interpretation of types as relations, but we're going to parameterize those by some relations which express some invariance on the heap, the mutable storage. And they all have, so here's my parameterizing relation for a function, and this sort of says, well, it says something about related arguments give you related results, but those things all get past a parameter, this delta and r, and there's a bit of quantification over future extended worlds, because you always have to say that two things are related. If at some later point when more things have been allocated, you're going to call them with related arguments at that relation. And there's a bunch of stuff, and you get a fundamental theorem. And honestly, the things we're studying here are really quite simple, in the sense that the operational semantics of these languages is not complicated, but the sophistication of the reasoning principles that we put on top is, well, as much as you like, to be perfectly honest. I mean, this is only the very basic version of this. You can add lots of bells and whistles. And you kind of follow this recipe. This is like, oh yeah, it's an index logical relation, follow the pattern, prove the theorem, blah, 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 blah. It took me, at least, a very long time to actually understand what's going on here, and the sense in which it kind of means what Peter and Bob said it meant back here. So I think some people have, so possibly some of you have worked with things like this, but still don't have quite the same understanding. So I'm going to try and tell you something that's interesting about it. So the crucial judgment is this one down at the bottom, which talks about things, the meaning of things being related in some context, right? And the essence of the way that this thing works is you've got your terms, and they've got access to some bunch of free things from the outside, from the context. And what this says, because the way that this parameterization works is it says that these things are guaranteed to preserve any relation on the store that is preserved by all the operations they have access to. So you preserve all the relations that are preserved by all the operations is kind of the key thing that's going here. And it's quite possible to work with these things for a long time without saying that explicitly, and I did. But once we had that realization, we were able to give the relational semantics for those effect systems that we've done in our ML compiler and use that to prove the correctness of those effect-based transformations very, very, very prettily. I'll make a small aside. When I was doing this work, I really didn't like this partial heaps and errors stuff that I saw in separation logic. It was like, it wasn't extensional. It was like, it was wrong, it's wrong, it's wrong, it's wrong. So we came up with an alternative story for how separation logic should work. And the idea is that we separate off, we'd say we'd have a relation or a predicate, and it had something which told you what locations it depended upon. And obviously what location something depends upon itself depends upon the contents of the state. Because, you know, whether or not you've got a list here, well, you have to actually follow the thing in the heap to work out what locations you touch to verify that. So the idea is you have a map from states to sets of locations, but that thing can't look at more locations than it's actually going to return as its answer. Right? So it has to be self-supporting in this apparently asymmetric but actually symmetric definition. And then we did this. And so we did a lot of work with this definition, which I liked better because it worked with total states, total heaps. But actually it turned out to work really badly because existential quantification doesn't work terribly nicely. And I got Matt to help me for one paper, and then I gave up and did it all the way that Pete had done it in the first place. So. So the other thing I was particularly excited about was applying these techniques to really low-level languages, not just wild programs, but things like machine code. And in particular, when we did this stuff, that stuff, you know, we're baking in the allocator, right? And in fact, here we baked in the allocator using some fancy domain theory, but then we still had to put a relation on the top, and that was really clunky. We got fancy domains with a thing that allowed you to deal with the fact that you couldn't tell names apart, and then we still put a relational quotient on the top of that already quotiented structure. And I thought we should be able to do everything in one place. So the idea here was to say, let's do separation logic, relational separation logic for machine code, such that we can actually specify and prove the allocator itself rather than having it being built in. So this was really, 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 really crude. We went right down to the bottom level, and we got this specification. And basically, the way that this works is it says that the allocator has some private invariant, and provided that the client promises to behave the same whatever fresh location it gets given, calling the allocator with a continuation back into the client promises to behave the same. So this is really rather elegant, and we proved some boring code, and then with Ivana, somewhere here, we proved a slightly more convincing allocator than this one. So we then applied the same techniques to give us semantics for types of a high-level language in terms of these relational separation logic judgments on low-level code. So the tensors here are separating conjunctions. And then even going to predicative stuff to specifying and verifying real x86 machine code all in Coq. So we actually even assembled the machine code in Coq so that you have the strongest possible guarantee. You can extract a bootable image from Coq and run it using a version of separation logic that works for low-level code. So then, in 2017, I moved to Facebook. Pete had obviously been there since 2013, working on infer and inventing incorrectness logic and founding the incorrectness logic lab that Benno and Josh here were both in. And I was supporting the hack team in London and some researchers over in Paris. And we were both keen on real verification, having done that sort of stuff outside. And Pete had already made links inside the company with people who might be possible customers for this. And so people on my team did do some successful formal verification in COC of some microkernel code that was being developed inside Meta, and this was really exciting. I think, is Noam here as well? Yeah, yay, Noam. Yes, it was awesome work. It was great. Unfortunately, the project got shut down very shortly after we'd done that, but that wasn't our fault. We successfully used Iris separation logic to verify some real code. And then, yeah, Pete moved on to Lacework, which was a big loss for us. And the researchers moved over to Pete's side of the org and merged with this incorrectness logic lab. And now I get to work with Jules and others on Infer and Pulse and doing incorrectness logic, and we're applying it to the hack language. And I will say, making the jump to under approximation and bug finding is actually surprisingly difficult. I find it a front to everything I do, but I'm gradually having my brain reprogrammed into thinking this way, though I am also very excited about the possibility of combining under and over in a non-trivial way. So yeah, that adds up to very nearly 30 years of work following in Pete's footprints, and I'll say thanks, Pete, and happy birthday.
We have time for some questions. I believe there's a gentleman down the front.
Speaking of scale, can you remind us how much hack code there is, and why are you applying this stuff to hack? Is there a business reason?
How much there is? Well, I think we say at least 100 million lines is cleared, but yeah, and some.
But what's the motivation for applying all this stuff to hack?
There's a bunch of things that the hack type checker can't do. And it's the most important code base in the company. So, more hack developers than any other sort of developer. Infer hasn't been able to touch it before. So there's a whole bunch of applications for things, firstly, language-based things that are outside the type checker. And then there's supporting code migrations and big global things where, again, you kind of need that interprocedural analysis in order to be able to validate the change.
Too revealing to answer, like, why now after 9 or 10 years of Infer at Meta? No? Okay, I didn't ask. I didn't ask.
Yeah, anyway. Well, I will say it's about time.
I think we have time for a couple more or one more. Anyone else? Okay, in that case, yeah. And let's thank Nick again. Thank you. I mean, one piece of context about the hack is that just about every Facebook developer or Meta developer uses hack at some point during their work week, whether they're working on hack as a sort of as the final end product for what the users are going to use, or whether it's just coordination stuff. Everybody does that, including me. I'd like to welcome Josh Bodine to the stage. I think he's still hooking up. Yes.
While we wait,
yes.
Explain what hack is.
I beg your pardon. Yes, of course. PHP is the language that Facebook was built on, and hack is a pretty strongly typed, I would say, version of PHP. I've only ever programmed in hack. Whenever I see raw PHP, it just breaks my head because there's no types anywhere. But Nick had a lot to do with the design of the type system of hack, and it's a really very impressive piece of work.